So I want to talk for a little bit about this theorem which you guys are proving in your homework, which says if a sequence is monotone and bounded, it converges. So this means that if a sequence is always increasing or always decreasing, then it has to be bounded. So the idea would be something like this. If you plotted the points, you know that they're bounded. Let's say that's the upper bound and it's increasing. Well, if it's always increasing, then it would have to get closer and closer and closer to that some point, right? Because it's always getting bigger, but it can't go past the bound, and so therefore it would converge. Same thing if it was decreasing. So I want to talk about how we can use this theorem in the context of series. Okay, so consider a sequence Bn, and then so here n is from 1 to infinity. Then we say that the infinite series associated with it would be when you add all of those terms up. Add all of those terms up. And because we're adding up an infinite number of things, there has to be some kind of limiting process involved in this. So the way we define the series converging is just like we did in calculus. A series, the sum of the bn's converges if and only if the sequence of partial sums converges. So the sequence of partial sums, and we're going to call those partial sums S. So S sub m will be the partial sum where we take B1 plus B2 plus B3 all the way up until we get to Bm. If and only if the sequence of partial sums converges to some number, we'll say B. And then if that's true, then we write that the sum of the bn's is also B. Okay? So in order to show that the sum of the bn's converges, what we're going to have to do is now show that the sequence of partial sums converges. So we can cast this back into the case of a sequence, which we know how to deal with. So what I want to do is look at how we can use this theorem, which says that a sequence is monotone and bounded, it has to be convergent, in order to show that a few series converge. So the first one that we're going to look at, let's go with example. We're going to show that the sum of the 1 over n squareds, when you sum n from 1 to infinity, we're going to show that this converges. So let's look at the partial sums and see what they are. Okay, so the partial sums are Sm, and we're going to add up, say, 1 plus 1 over 2 squared plus 1 over 3 squared up until we get to 1 over m squared. Now, since the 1 over n squareds are always strictly positive, the SMs have to be increasing. So we know our sequence is increasing. The question is our sequence bounded? So is the sequence, oops, let's not do bn's, but is our sequence of partial sums bounded? If it is, then we know our series will converge. So let's take a look at these partial sums and see if we can show that they're bounded. So let's look at Sm. Remember that was 1 plus 1 over 2 squared plus 1 over 3 squared, and that will go up until we get to 1 over m squared. And what I'm going to do is this. Let's write this out just a little bit. This would be 1 over 2 times 2 plus 1 over 3 times 3 plus 1 over 4 times 4, all the way up until 1 over m times m. I can make this smaller, bigger, by making the denominators smaller. The denominator gets smaller, the fraction gets bigger. If I do that for all of them, the whole sum will get bigger as well. So I'm going to write this as 1 plus, I'm going to replace one of the 2's in this first term with 2 times 1. So one of the 2's got bigger, it became a 1, so denominator is smaller. Do the same in the next. I'll make one of the 3's 1 less, so 1 over 3 times 2. 1 over 4 times 3, so always just 1 less for one of the terms. And then this last one will be m minus 1 times m. Now, how is that useful? Well, I'm basically going to think of this as coming from the difference of two fractions, and so I'm going to kind of undo the subtraction and common denominator. I can write 1/2 as 1 minus 1/2. I can write this 1 over 3 times 2 as 1/2 minus 1/3. Notice that if I cross multiply, I would get 1 times 3 is 3, minus 1 times 2 is 2, so that's 1 over 3 times 2. Plus, now I can do 1 over 3 minus 1 over 4 until I get to the end, and this one will be 1 over m minus 1 minus 1 over m. Now, the advantage of writing it that way, which probably wasn't at all apparent why I wanted to do that, is that now we can see that this is in fact a telescoping series. So I have minus 1/2 and plus 1/2, minus 1/3 plus 1/3, minus 1/4, there would be a plus 1/4. So all of these terms are going to cancel except the 1 here at the beginning. There's actually 2 of them, so 1 plus 1. And then the very last term, which is minus 1 over m, which is the same as 2 minus 1 over m. Well, guess what? All of those have to be less than 2 because you have 2 minus something that's positive. So what does that tell me? Well, this tells me that my SMs are monotonic and bounded by 2. So all the SMs have absolute value less than 2. Thus, let me say this, the sequence of partial sums converges. Well, what does that mean? Well, that means that our original series converges as well. Now, of course, we didn't answer the question, what does it converge to? So we'll have to think about that maybe at a later date. But for now, we just know it converges, and typically that's sufficient. That's the piece that we really want to know. So let's look at one more example here. Let's look at the sum from n equals 1 to infinity, 1 over n. Hopefully this series is familiar to you from Calculus 2 and maybe other places in your math education along the way. This is called the harmonic series. The harmonic series. So let's look at the partial sums here. So our partial sums SM will be 1 plus 1/2 plus 1/3 plus 1/4 and so forth up to 1 over m. Notice that these are still increasing because each time we go to the next m, we add something positive, so it has to be getting bigger. So it is monotone. So the only question is now if it's bounded. If it's bounded, then we would know this sequence of partial sums converges, and therefore the series that we're interested in converges. So let's take a look at some of these partial sums. So let's look at S4. Let's look at S4. S4 would be 1 plus 1/2 plus 1/3 plus 1/4. And notice that this is greater than, I'm going in the other direction, 1 plus 1/2 plus 1/4 plus 1/4. Instead of adding a fourth, I added a third, I added less. made the denominator bigger in this case. Notice that adds up to 2. So in this case, our partial sums are not bounded above by 2 anymore. So therefore, that doesn't mean there's not a bound. It just means, you know, our candidate from last time doesn't work. So we could kind of keep playing with this a bit and see if there was a bound. So let's look at this. We're going to look at a partial sums of a very specific form. We're going to look at all the partial sums where they're the form s sub 2 to the kth power. So this would be like s sub 4, s sub 8, s sub 16, s sub 32, etc. So that's what we're going to look at here. So this would be terms that look like the following. It would be 1 plus a half plus a third plus a fourth plus, and this will go all the way out until we get 1 over 2 to the k. Okay, so just a special form there. And now I want to do a little bit of kind of a grouping of these terms. So I'm going to leave the 1 alone. I'm going to leave the 1/2 alone. But I'm going to group together both the 1/3 and the 1/4. Now I've grouped 2 together. The next grouping is going to actually have 4 together. It's going to be 1/5, 1/6, 1/7, 1/8. Notice I went up to that next power of 2, then I went up to 4, and then I went up to 8. The next one will go up to 16, right? So the kind of last set here would be 1 over 2 to the k minus 1 plus 1. So 1 past that. So like here, we're at 1/8. The next term would be 1/9. And then we would go all the way until we got to the 1 over 2 to the k. So each grouping has more and more terms inside of it. Now, why in the world would I want to do that? Well, remember how we did S4? We replaced some of the terms with something that was smaller. So in this case, I'm going to say it's greater than 1 plus, I'm going to leave the 1 alone, I'm going to leave the 1/2 alone. But now I'm going to go to these two I grouped together. I'm going to replace every term with the smallest in the parentheses. So that first term, that 1/3, I'll replace with 1/4. It was the smallest of 1/3 and 1/4 in the parentheses. So I replace both terms by that. That makes it smaller. If I go to the next one, the smallest term in this set of parentheses is 1/8. So I'll replace the first 3 terms with 1/8. That makes the quantity on the right smaller, which is what I was aiming for. And the last 1/8 stays the same. Do that until I get to the very end. This last one I'll replace with 1 over 2 to the k plus 1 over 2 to the k plus all of those get replaced with that smallest term, 1 over 2 to the k. Now, why is that helpful? Well, let's take a look. I have 1 plus a half plus, well, add these two together. What do I get? I get 2 times 1/4. Well, what do I get over here? I get 4 times 1/8. What do I get in this very last one? I would have how many of these? Well, I would have 2 to the k minus 1 of them, and each of them is 1 over 2k. So, what's the advantage here? Well, if you multiply all these together, you get precisely 1/2. 2 times a fourth, 1/2. 4 times 1/8, 1/2. You cancel out the powers of 2, what are you left with? 2 to the minus 1, or 1/2. So this is 1 plus, there are k, you can count those up there, k, 1, 2, 3, 4, all the way up there, k 1/2. Well, what happens? That's not bounded, because that goes to infinity as k gets big. So what does that mean? It means that my sequence of partial sums, is unbounded. Oops, partial sums. Why is that bad? Well, since convergent sequences are bounded, the harmonic series must diverge. And of course, this is something hopefully you remember from calculus, calculus 2, that the harmonic series diverges. So keep in mind, the thing about the harmonic series, it's of a kind of a special form. Both series where they're 1 over n to a power. The harmonic series is that breaking point between convergence and divergence. 1 over n, where the exponent is anything greater than 1, converges, but if it's less than or equal to 1, it diverges. That's that breaking point. This just kind of shows us something bigger does converge and something less than doesn't. But it also gives us some sense of how we would actually go about showing such a thing happens, and why this theorem that bounded monotone sequences is so important. So hopefully that was kind of interesting and puts this theorem that we're using into context a little bit about how we might use it. And we probably won't have a lot of homework questions about series, but I wanted you to see series. I wanted you to see and remember how they connect back to series, and how some of these theorems that we can be that we're proving can be useful, not just in the context of series, but also in some other interesting applications as well, like series.